Hello dear students, welcome to Pen and Paper Chemistry on YouTube. Lesson 4 D and F block elements. And as you can see, I've got the D block elements listed here and a part of the F block wherein I've just taken the lanthanides. Why have I done this? So that you are able to relate to what we are going to talk about today, and we are talking about lanthanoid contraction. We had spoken when we had said 3D series that the atomic radii actually decreases on going across. Of course, there are anomalies. We've already spoken about that. Let us observe the variation when you go down. If you notice 3D to 4D series. This is actually period number 4, but this is the 3D series because the electrons are entering into the 3D orbital, right? So 144, 162, 169, good so far. Go on, 132, 145, 144. You notice that although we are adding an electron, an extra energy level is being added. Here the valence shell is the 5th one, here the valence shell is the 6th one. So although an extra energy level is getting added, we notice that the atomic radii does not increase much. In fact, it almost remains the same and is actually showing a decrease. Here, along with each of the element, I have listed the atomic radii in picometer so that we are able to understand from the table itself. Everywhere we will see that the atomic radii remains the same, or it changes, or it increases or decreases, but we never bother to see the values. Once you see the values, you know, it's much easier for you. Go on to the next one. Group number 5, 122, 134, 134. See, they are same. 117, 129, 130. So although on moving from 3D to 4D series, we notice that there is an increase in the atomic radius. We do not observe a similar behavior when we are moving from the 4D to the 5D series, right? This is something odd. What is happening over here is, we have not got to notice this lanthanum. Now from this lanthanum, we've got elements with atomic number 58 to 71 listed over here, and these are put separately at the bottom, what we call as the F block elements. And as I said earlier, I have listed only the lanthanides. Let us observe what is the change in their atomic radius. 183, 182, 181, 181. So there is a decrease, right? As you are going across, there is a decrease. But is that decrease substantial enough as you are observing in the case of n is equals to 4 and n is equals to 5? Just see the values carefully. Forget about the last element because there you have fully filled orbitals, so definitely their behavior will be different. But you notice there the difference over here between yttrium and zirconium and niobium compared to what you are observing over here. If I take in simple in terms of numbers also, here's a difference of almost 15, almost 10 difference in terms of just plain numbers, right? 10 picometer, whereas here there's a difference just of 1 picometer. So of course, there are anomalies over here, but then if you notice in general, the decrease in the atomic radius when you are going across in the lanthanide series is not as much as you would expect from the behavior of the atoms that you have studied till now, right? And this is what we call as lanthanoid contraction. We have spoken about atomic radius. A similar behavior is seen in the case of ionic radius as well. 103, 101, 99, 98, 96, 95, 94. You see over here? What accounts for this behavior? So first of all, we will define, we say that lanthanoid contraction is nothing but the decrease in the atomic radius and ionic radius of lanthanides on moving from cerium to lutetium, which is much lower than expected. The difference, the variation is much lower than expected. right? So how does this affect over here? And why does it happen? That is because if you notice in the case of lanthanides, so how do we write the electronic configuration? Here the electron is entering into the F orbital, right? Now before I turn to full screen, I would request you to make a note of this chart. It is really useful to understand what you are reading, and you will not feel the need to memorize anything. This is from experience, I am telling you. I used to detest teaching this particular topic. Now I love it because it's so simple to teach as well. Only thing is, please remember, you don't have to learn these values, but you need to see this chart in order to understand, and making this chart is only a matter of 5 minutes. 5 minutes, you have these values and this will be clear to you. So please make a chart and also get your pen and paper ready, because I'm going to explain this lanthanoid contraction in further detail. So what is lanthanoid contraction is listed over here. What is so special about this? The decrease is not as expected from the increase in nuclear charge. We notice that as we are going down or as we are going across in this lanthanide series, the nuclear charge is increasing because the atomic number is increasing, right? Along with it, the number of electrons is also increasing. So the atom should shrink, right? If the valence shell and should go closer to the nucleus. But what we observe in the case of lanthanides is that you've got the nucleus in the middle, you've got the electrons moving around in the orbits outside. This is my valence shell. This is my penultimate shell, right? We have already spoken about this when we were discussing d orbitals, the d block. So this is the penultimate shell. In the case of F block elements, that is the lanthanides and the actinides, we notice that the electron is entering into the F orbitals of the inner penultimate shell, or also called as the antepenultimate shell. So what does it do? How does it make a difference? Again, coming back to shielding effect. Here, the electrons which are closer to the nucleus are selfish. They do not allow the nucleus to exert its attraction or to exert its pull for the electrons which are present in the orbits further away from it. They prevent it, they come in the way. And this is what we call as shielding effect or the screening effect. But the F electrons are not as selfish as the S, P or D, with the result. And why is it so? Because of their diffused shape. And because of their diffused shape, they do not prevent the attraction from reaching the valence shell as much as the S, P or the D orbitals. So the nucleus is able to pull the electrons inside, but not as strongly. With the result, we notice that the two effects, that is the shielding effect and the nuclear charge, they are balancing each other, causing the atoms, causing the elements in the F block to be closer in size. And what happens over here is the decrease in size is not as much as we would expect. There is definitely a decrease, but it has its effects on the D block elements. What is that effect we are observing is, just now I mentioned, please keep your charts handy. Just now I mentioned that as you are going down from the 4D to the 5D series, the atomic size is remaining almost the same, right? Exact same. Niobium and tantalum is 134. So this is attributed to the 15 elements which are coming under lanthanides, because this part of the periodic table should be fitting here. In order to have systematic presentation, that is why we have shifted it down. So because of these 15 elements, it affects the atomic radii of the elements after them, because in all these elements the electrons have already entered into the 4f orbitals, right? So let us see what are the other effects that we observe. Please make a note of this, and your lanthanoid contraction is on the way. So what are the effects of lanthanoid contraction? One we've already discussed. As we move from the elements of 4D series to the 5D series, the atomic radius remains almost constant. So what does it do if it is remaining constant? Because atomic radius is remaining almost constant, we will find it difficult to separate the elements of the 4D and the 5D series. A very, very common example is zirconium and hafnium. We saw in the table that the atomic radius of the two is exactly the same. So we had 145 and 144. These two are not easily separable, right? Same way if you see the other elements, so what we find is the elements of the 4D and the 5D series are found to be usually existing together. Now because the nuclear charge is increasing but the atomic size is either remaining the same or it is actually very, very less compared to the expected increase, we notice that the ionization enthalpy will also increase with the increase in the nuclear charge. The basicity of lanthanides. Now the lanthanides, starting from lanthanum, is also studied as part of the lanthanide series only because of its characteristics. So from lanthanum to lutetium, we notice that the basic character decreases because of the variation in the atomic radii. Because smaller size means the covalent character will be more. Lastly, we have the hardness, melting point, boiling point will also increase from left to right. Why? Because the atomic size is actually becoming smaller. The force of attraction, the bonding, the overlapping between the orbitals will be stronger because of this, right? So that brings us to the end of lanthanoid contraction. Next lesson we will be taking up some properties and I will be giving you a simple flow chart in order to study the properties of lanthanides. So stay connected for lesson number 5, and I hope you have started your concentrated study and a more focused study because the exams are now approaching nearer. Study regularly but stay calm.